Hello and welcome to the presentation on Zener diodes here. Zener diodes are deliberately heavily doped and carefully doped so that it is having very sharper reverse breakdown voltages. The forward bias characteristics of this Zener diode are similar to the conventional diode. The symbolic representation of this Zener diode is represented as shown in the circuit diagram here and is represented by the letter Z here. The anode A is of the P type and cathode K is of the N type semiconductor material. Now when this anode is connected to the positive terminal of the external battery and cathode is connected through this resistance to the external battery negative terminal, this Zener diode is said to be forward biased and the characteristics are exactly similar to that of a conventional diode as shown in this graph here, wherein the conduction will be starting the linear variations in the current with respect to the voltage between the anode and cathode, and that point is even called as the knee voltage point. When the diode is connected in the reverse pattern, that is, the anode of this diode is connected to the negative terminal of the external battery and cathode of the Zener is connected to the positive terminal of the external battery, the Zener diode is said to be in the reverse bias configuration. Now, in this reverse bias configuration, if we plot the graph of the variations of the reverse voltage across this anode and cathode, as mentioned here in the negative voltage axis minus VAK, the variation of the Zener current which is going from this cathode to the anode here represented in the negative current axis as IZ here. The characteristic plot is similar to that of a conventional diode. The only change is that at Vz, which was earlier called as the VBR, the reverse breakdown voltage for a conventional diode, it is named as the Zener voltage. At this point, there will be a sharp rise in the reverse current, and the voltage Vz is almost maintained constant throughout this range of Iz minimum through this Iz maximum. And this range of the characteristic is called as the Zener active region. And this region, as usual, is called as the reverse saturation region. And the Zener will be not in action in this particular region. As the Zener is put into the reverse breakdown voltage here, it maintains the constant voltage Vz across the anode and cathode with a range of variation of the Zener current between Iz minimum through this Iz maximum. This reverse breakdown region is the active operating region of the Zener diode, and the Zener is said to be in action and it will be in the on condition in this region only. Due to this beautiful characteristics of the Zener of maintaining the constant voltage across its terminals with a range of variation of the current through this Zener diode is used as the voltage regulator element in the voltage regulator circuit of some of the lower range electronic devices. And even this Zener diode is used as the standard voltage reference element in some of the electronic circuits. Now, we will see how this Zener will be working as a voltage regulator. First of all, what is the meaning of this voltage regulator? Voltage regulator is a circuit which maintains the constant output voltage across its load terminals, irrespective of the fluctuations or changes in its supply voltage and fluctuation and changes in the load resistance also. This characteristics of maintaining a constant voltage, output voltage across the load resistance is called as the voltage regulation. In this circuit, Zener diode Z along with the series resistance Rs take the major active role in maintaining the constant voltage V0 across the load resistance RL terminals here. Again, the same graphical representation is retained for your reference, and this oval indicates that it is the active region of the Zener. Zener will be in action only in this reverse breakdown area and nowhere else in this saturation region and also in the forward biased region. Now, you can observe the point P here in this circuit. You can observe the point P. Before continuing, you can pause the video and observe all the notations that we have used. The current flowing through this series resistance Rs is the supply current Is, the load current IL which is flowing through this RL. IL into RL is called as the output voltage which is equal to V0, and the Zener current which is flowing from a cathode through this anode and returning to the supply voltage here. Now, we are having a node here at this point P. By Kirchhoff's current law at this node P, we can write Is is equal to sum of the currents Iz and IL, and we will call it as equation number 1. Now we are having a mesh here, means the loop. Kirchhoff's voltage law is even called as the Kirchhoff's mesh law. Second law we call even it as. Now, for the loop here, having the voltage source V, the series resistance Rs, the load resistance RL, we can write the Kirchhoff's voltage law for this particular path of the loop here. And according to this Kirchhoff's voltage law, we can write this equation. V is equal to Is into Rs plus IL into RL. And we call this as equation number 2. As this load resistance is directly connected across this Zener diode, the Vz, the Zener voltage, is always equal to the output voltage V0. That you should clearly mention in your notes. Now, in this circuit, there can be two variations possible. One is that the supply is fluctuating, means supply is changing a little bit. It may rise a little bit or it may decrease a little bit. Even under these such variations, the output voltage V0 should be maintained constant. Then only we say that the circuit is regulating the output voltage. On the other hand, in the second case, where this voltage is constant, that is not varying, But due to the switching on and off of the load elements, this load resistance may vary. It may either increase or decrease. With this particular condition of operation of rise or fall in the load resistance RL, there should be no change in the output voltage V0. Then only we say that the output voltage is regulated. Zener diode along with this series resistance RS is beautifully controlling this voltage regulator action in the circuit. We will analyze the working of this circuit in two cases. The case 1, when the voltage, supply voltage V is changing, means fluctuating, and RL, the load resistance, is fixed. What happens? With the change in this voltage V, if the voltage is raised, that will lead to the rise in the supply current also. Therefore, it leads to the rise in IS. As this IS, the supply current, is increased, the voltage drop across this RS, which is equal to IS into RS, that will also be increased. With the rise in this supply current IS, according to the equation 1 here, IZ and IL sum is disturbed there. But there is no change in this load resistance. Therefore, the load current is fixed and it will not take any extra current. Therefore, the excess current which is raised due to the rise in the supply voltage is diverted through the Zener diode. Instead of working at the lower current ranges here, the Zener now starts working at the higher current range, still maintaining the same voltage across the Zener. The Vz is still maintained same. That is why V0, which is always equal to this Vz in this circuit, it is also maintained constant. Again from the equation 2, where the rise in this V is compensated by the equivalent rise in the voltage drop IS into RS, and maintaining the product IL into RL, which is equal to V0, the load resistance, is still maintained constant. This is how the output voltage is regulated at the constant level in the case 1 here. Now, going through the other case. The case 2, when the supply voltage is maintained constant and there is a change in this load resistance RL. If there is a change in this load resistance RL, say the load resistance is increased. With the increase in resistance, the load current decreases here. Therefore, it leads to the decrease in the load current here. With the decrease in this load current and there is no change in the supply voltage V, there will be no change in the supply current IS. As there are no changes from the supply area, according to this equation number 1, IS is unchanged, but IL is decreased. To balance this equation 1, IZ will increase. The excess current will be diverted through again this Zener diode, maintaining the equilibrium of this equation number 1 here. With this fall in this load current, the Zener current rises. The explanation just you have heard of this. Now, the Zener, which was assumed to be working at this lower current range, it will be now working at the higher current range here. But again, In both the range of this Zener currents, the Zener voltage Vz is maintained constant. Once the Vz is maintained constant, which is always equal to the V naught, the output voltage in this circuit, it is also maintained constant here. You can observe here, according to this equation number 2, as there is no change in this V and no change in this Is, there will be no changes in these two elements of the equation 2. As V and ISRS are unchanged, it is mandatory that the product IL into RL, the product of load current and load resistance, which is equal to the output voltage, which is also not changing. And this is how the output voltage V0 is maintained constant in the second case also. In both the cases of the variations of supply voltage and variations of the load current, means the load resistance, Zener diode along with the series resistance takes a very important role in maintaining the output voltage V0 constant. This is how the Zener is put into the action of voltage regulator in this circuit. In the next video, we will see further summarization of this whole unit.